This video is on section 6.4 notes, the central limit theorem. So previously, for data with a normal distribution, we converted our random variable x to z by standardizing it. This allowed us to use the standard normal distribution table. Now, we're going to learn that for any population with any distribution, whether it's uniform or skewed or bimodal, the distribution of sample means x bar can be approximated by a normal distribution when the samples are large enough, when n is greater than 30, and that's what the central limit theorem states. So as long as we have a sample size that's getting larger, we're going to have a sampling distribution that is approximated by a normal distribution. So here's an example, so you guys can see that in action. Pictured below on the left is a histogram of 1,000 Boston commute times in minutes, and this is from dataset 31 in Appendix B, if you're curious to see it. Pictured on the right is a histogram of 1,000 sample means, where each of the 1,000 samples includes 50 Boston commute times. So here this is definitely a right skewed distribution. The skew is to the right, and then here when you look at the sample means, you can see that this is approximately normal. It's definitely unimodal, right there in the middle, but it's approximately normal. So this is another example just so you can see kind of what's going on and how this works, or how to recognize what the central limit theorem is actually saying. And then once we understand what it's actually saying on this first page of notes, then we're going to do some examples where we actually use it. So this example right here is not something that you're going to be practicing or doing over necessarily. This is just to understand what the central limit theorem is even saying. So it says, draw a histogram that represents the probability distribution for a fair die. A fair die has a mu, or a mean, of 3.5 and a sigma, or a standard deviation, of 1.7078. So first we'll define what our random variable x is. X is going to be the result of a single roll. And that means that for this, our sample space is 1, 2, 3, 4, 5, and 6. So if we draw a histogram that represents that, and we put x along the x-axis and the probability of x along the y-axis, then we know 1, 2, 3, 4, 5, and 6. We know that this is going to be a uniform distribution, and that the probability that we roll a 1 is the same as the probability that we roll a 2 is the same as the probability that we roll a 3. So here's what our histogram looks like. And so the probability that we roll each of these numbers is 1 out of 6. A die would be 6-sided. Each of the numbers has a probability of 1 out of 6 of being rolled on a single roll. So this would be an example of not this histogram exactly, but the original set of data that we're talking about that could be any distribution. It could be normal, but it could be right skewed, it could be left skewed, it could be uniform. In this case, the graph of the histogram is a uniform distribution. And so now we're going to draw a histogram that represents the probability distribution for 2 fair dice, which is going to be the sample means. And then you'll see how once we look at the sample means, it's going to more closely resemble a normal distribution instead of a uniform distribution. So you can see how it works. So if we have 2 fair die, we're going to say that x bar, or the sample mean, in the sample of 2 die, or 2 dice, this is the mean result per die, and that will make more sense in a minute. So what we're going to do is draw a table to help us figure out all the possible results if we roll 2 die. Roll 2 dice. Sorry, plural, dice. Roll 1 die, roll 2 dice. Okay, so if I roll a 1 and a 1, that means I got 2. If I roll a 1 and a 2, that means I got 3. 1 and a 3, that means I got 4, 5, 6, 7. If I roll a 2 and a 1, that means I got 3. A 2 and a 2 means I got 4. A 2 and a 3 means I got 5, 6, 7, 8. A 3 and a 1 means I got 4. A 3 and a 2 means I got 5, 6, 7, 8, 9. If I roll a 4 and a 1, I got 5. A 4 and a 2, I got 6, 7, 8, 9, 10. If I roll a 5 and a 1, I get 6. If I roll a 5 and a 2, I get 7, 8, 9, 10, 11. If I roll a 6 and a 1, I get 7. If I roll a 6 and a 2, I get 8, 9, 10, 11, 12. Okay, so for each of these, you can see that there's a varying amount of ways I could get that roll. So for a sum of 2 and a sum of 12, there's only one way out of all 36 ways. There's only one way I could get each of those sums. So for 2 and 12, I have a probability of 1/36. For the 3s and the 11s, there are 2 ways I could get each of those. So 3 and 11 is 2 out of 36. For the 4s and the 10s, 3 out of 36. For the 5s and the 9s, I have 4 out of 36. For the 6s and the 8s is 5 out of 36. And then for the 7s, that's 6 out of 36. Now, these sums are based on 2 dice, and so what I want is to find the mean result per 1 die. And so I'm going to say X bar is the mean per die. So 2 and 12, if that was 2 dice, then for 1 die, that would be 1 and 6. Has a 1 out of 36 chance. If 3 and 11 were for 2 die, then that would be 1.5 and 5.5 for 1 die, the mean per 1 die. For 4 and 10, for 2 dice, then it would be 2 and 5 for 1 die. 5 and 9 for 2 dice, that would be 2.5 and 4.5 for 1. 6 and 8 would be 3 and 4 as the mean for 1 die, and then 7 would be 3.5 as the mean value for 1 die. So if we go through and we graph this, I'm going to label 1, 2, 3, 4, 5, 6, and then along this side I'm just going to go every 2. So this is 2 out of 36, 4 out of 36, 6 out of 36. So there's your X bar, there's your probability. The probability of getting a 1 is 1 out of 36. 1.5 is a 2 out of 36 probability. 2 is a 3 out of 36 probability. 2.5 is a 4 out of 36 probability. 3 is a 5. 3.5 is a 6 out of 36 probability. Okay, and then 4 is a 5 out of 36. 4.5 is a 4. 5 is a 3. 5.5 is a 2. And 6 is a 1. So if we look at the mean for both of these, the mean is the same. You can see that the middle for this is 3.5. You can see that the middle for this one, mu of x bar, is also 3.5. The big difference is the standard deviation. So the standard deviation for this one is 1.7078, and so that talks about the spread. Remember, the standard deviation talks about the variation of the data. Here, our standard deviation is going to be smaller because our data doesn't vary as much. This went from a uniform distribution to a unimodal distribution, and we only had 36 data points. It's more than 30, and so the uniform distribution is starting to approach a normal distribution, and the more and more data points that we have, the more it will approximate a normal distribution. So if we did this next and we used 3 dice, we'd get even closer to a normal distribution. If we did 4 dice, we'd get even closer. So as we add more and more pieces of data, we would get closer to a normal distribution. Now, to calculate the standard deviation for the probability distribution of the sample means, you say sigma of x bar, and you take sigma and divide it by the square root of the number of trials, or the number of samples that you have. And so for this, we would do 1.7078 divided by square root 2, because we had 2 die that we were looking at, or the outputs of 2 die. And we'll go ahead and calculate that. 1.7078 divided by the square root of 2. And so we can see that the standard deviation for the sample means, standard deviation of x bar, is 1.2. which fits what we're seeing in the graph. We're seeing that this graph has a little bit less spread than this histogram did. All right, now we're not going to repeat that. That was just so that we could understand what the central limit says. What it's getting at is that if you start with one type of distribution, it is possible to then take some data and look at the sample means and approximate a normal distribution. And the benefit of that is just that we can use our standard normal distribution table. That's truly just the benefit. So here on the next page, if you were confused by that example, that's totally fine. We are about to say, well, if I have a problem that works with the central limit theorem, how do I actually use it? That's what the next 3 examples are going to accomplish. All right, so this first example says, suppose the overhead reach of adult females is normally distributed with a mean of 205.5 centimeters and a standard deviation of 8.6 centimeters. And we're thinking overhead reach like literally you put your arms above your head. How high can you reach above your head to get something out off a shelf, or maybe you're on an airplane and you're trying to get something out of an overhead bin or something like that. If one adult female is randomly selected, what is the probability that her overhead reach is less than 204.3 centimeters? The way this question is phrased, if one adult female is randomly selected, her overhead reach, and this says normally distributed, this question is phrased exactly like section 6.2. So that first question is exactly what we've done before. What is different is if it says if 36 adult females are randomly selected, what is the probability that their mean overhead reach is less than 204.3 centimeters? And then after we calculate that, this is the one that's going to make us interested in the central limit theorem. After we're going to calculate that, we're going to say, does applying the central limit theorem to this situation make sense? Right, so the first thing we're going to do is set up both problems and kind of write them in parallel so you can see the similarities and the differences. So first we're going to define our variables. So x, for that first question, if one adult female is randomly selected, what is the probability that her overhead reach is less than 204.3 centimeters? We're going to say x is the overhead reach of one adult female. And then x bar, the mean of the sample means, is going to be the mean overhead reach of a sample of 36 adult females. So if we look at this, the requirements is to make sure your population has a normal distribution or that your sample size is greater than 30. So here they say we have a normal distribution, so we already know we can use it. We also have a sample size that's greater than 30, so we've got both requirements met there. All right, so here it says if one adult female is randomly selected, what is the probability that her overhead reach is less than 204.3 centimeters? So if we were doing this problem in section 6.2, we would say, okay, I don't have a table for the random variable x, but I do have a table for z. So let me go ahead and convert this into a z-score, and I would use my z-score formula. And I'm going to write my regular z-score formula up here, which is x minus mu over sigma. And so we've got 204.3 minus the mean, which is 205.5, over sigma, which is 8.6. Okay, so I can type that in. 204.3 minus 205.5 over 8.6. So the standard deviation is negative 0.14. And so now that I've standardized this problem to a variable of z, I can grab my standard normal distribution table, look for negative 1.4, 0.4443, and that's the probability. So what is the probability that her overhead reach is less than that? The probability that her overhead reach is less is 0.4443 or 44.4%. Okay, over here. What is the probability that if 36 adult females are randomly selected, their mean overhead reach or their average overhead reach is less than 204? So here we would say the probability that x bar, that their mean is less than 204.3, And again, we're going to standardize this. We're going to create the z-score so we can use the standard normal distribution table. However, the z-score is created a little bit differently. We're going to use the sigma of the sample means, and that sigma uses the formula sigma over the sample size. So z is going to be x bar 204.3 minus the mu value, or the mean. Sorry, that was the sample mean. Sample mean divided by the normally distributed mean over the sigma, which is 8.6, divided by the square root of the sample size. So we're going to type in something real similar, 204.3 minus 205.5 divided by 8.6 over square root 36. Negative 0.84. So here we're finding the probability that z is less than negative 0.84. And I'm going to use the table, negative 0.8, negative 0.84 is 0.2005. Okay, now here where it says, does applying the central limit theorem to the situation even make sense? You have to answer the question, does it make sense to, in this context, talk about individuals? Or does it make sense in this context to talk about the group and the average or the mean of the group? Which one do you care more about? So when we look to see if the central limit theorem should apply, you're always going to ask yourself, whether it should apply to an individual person, the answer to this question, or to a group. And that's going to determine which of these scenarios you're going to calculate to answer a question. So here, because of the way the questions were phrased, we calculated both. But typically, if they're asking about an overhead reach of a female, and they're talking about reaching things on the shelves or reaching things in an airplane or something like that, we're not worried so much about the group. Can the group do it? We're worried about individual people. When we build that house and make the shelves that high, can an individual person get to the shelf, or is that going to be a complaint? People have to buy some sort of stool so they can reach the shelves. If we build an airplane, is the average woman going to, as an individual, going to have trouble reaching that overhead bin, so it slows down everybody behind her getting on the plane? That's going to be an issue. So the answer to this is no. The central limit theorem should not apply because the central limit theorem applies to groups, and this is a question where we would care more about individual people. And it seems a little bit abstract to answer that with this first question, but as we answer some more questions, you'll start to see like, oh, I can understand the individual versus the group scenario. All right. The next situation says an elevator has a maximum capacity of 3,125 pounds. Suppose the elevator is loaded with 16 men. If the weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 4.8 pounds, would you want to be on the elevator? Does applying the central limit theorem to this situation make sense? So here, they're not asking us one question versus the other where we would think, oh, that's section 6.2, and then now the central limit theorem. They're just asking us a question, and we have to determine, well, should we use the information that we would use in section 6.2? Should we solve it that way? Or is this a situation for the central limit theorem? So this is a situation where we would say, does it make more sense to find the weight of a single man? Or does it make more sense to look at the weight of a group of men to see how safe this elevator is going to be? What's the probability that this elevator is going to have a group of people that are less than the max capacity, or the probability that this elevator is going to have a group of people that are more than the max capacity? So here it says there's 16 men in the elevator, and so we want to figure out what the max capacity is for one of those men because that's the theoretical data point that we're going to be using. So I'm going to write down my variable first. We have over here, we have the weight of one man. This is if the individual person is the way that it makes sense to solve the problem. Over here we have X bar is the mean weight of a sample of 16 men. So if it makes the most sense to look at the weight of an individual man, then we're going to use the methods we learned in section 6.2. If for the elevator, it makes more sense to look at the average weight or the mean weight of 16 men, then we're going to use the central limit theorem. So when we look at this, we know 3,125 pounds divided by 16 men . 195.3125, and I'm not going to round that because anytime we have decimals that are easy to write down like that we can use in our computations, it's going to make our final answers more accurate, so I'll just use the whole thing. So here, if you're talking about an elevator, I'm not worried about an individual person riding an elevator unless that individual person is above the max capacity. What I'm worried about is the group of 16 men underneath that max capacity, or on average, would a group of 16 men be beneath the average weight if we were to consider a man who has a thinner build with a man who has a stronger build or a bigger build that's more burly. So that's what we want to look at. We're not so much worried about an individual man as we are worried about the group of men and what their average is or their mean is. So here we're going to say if the individual matters, use section 6.2 method. And this is exactly what we did up here. They are not the one that matters in this case, so we're going to cross that out. If the group matters, use the central limit theorem. And I'm going to put check there because that's what we're going to do. Okay, so we're going to say, let's find the probability that the mean weight of the entire sample of men is less than 195.3125. If the average of the sample of men is less than that, then they are safe on that elevator. We're not worried about them crashing because they are less than the max capacity. So we can't use this right now. It's a random variable x. We need z, so we can use our standard normal distribution table. So I'm going to calculate the z-score. I'm going to do 195.3125 minus 182.9 over standard deviation, which is 40.8, over the square root of 16. And in this case, we had a sample size of 16, which is less than 30, but it's okay because we have a normal distribution. They said either the population has a normal distribution or is a large group, bigger than 30. So here we're not worried about it because we do have a normal distribution, which is what was stated in the problem. All right, so the z-score for that random variable x is 195.3125 minus 182.9 over 40.8 divided by the square root of 16. So this z-score is 1.22. Okay, so the probability that z is less than 1.22, we got 1.22 is 0.8888. Okay, so this is the probability that the elevator is under the max capacity. And maybe you're comfortable with that. Maybe 0.8888 is comfortable to you, but that means 1 minus 0.8888. That means there's an 11% chance that that elevator is above max capacity. So I would say I don't want to be on the elevator because there's 11% chance that there's too much weight on the elevator if 16 people are on it, 16 men are on it. So central limit theorem does make sense because the group weight, the group average is what matters in this case, and I would not want to be on the elevator because the probability that it's safe is only 0.8888 or 89%, and that's not high enough for me. I want something as close to 100% safe as I can. Okay, one more question. This says a ski gondola bears a plaque stating that the maximum capacity is 12 people or 2,004 pounds. If the weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds, so that same mean and standard deviation as the last example, what appears to be the maximum weight per person for the gondola if 12 people are using it? What is the probability that a randomly selected man weighs less than the maximum weight? What is the probability that a full gondola will be safe? So this is essentially exactly the same as the last question. They just phrased the questions a little bit differently. So we're going to start off by identifying our variables. We're going to say X is the weight of one man. X bar is the mean weight of a sample of 12 men. And then to determine if we can use the central limit theorem or if we should use our method from section 6.2, we just have to think, do we want to talk about an individual man and what his weight is, or do we want to talk about the average or the mean weight of a group of men when we're talking about this context? And here we would want to look at the group. We want a group of men that are going to be safe riding a ski gondola. The individual weight of one man doesn't really matter because it just has to balance out with the other people that are on the ski gondola with him. So we don't care about the individual in this case. The individual doesn't matter. In this case, we're worried more about the average of the group. So it says what appears to be the maximum weight per person for the gondola if 12 people are using it. They didn't ask that question in the last problem, but they could have. They could have said if the elevator allows 3,125 pounds for a group and there's 16 people, what's the maximum weight per person? So here we just need to figure out what the average weight per person really should be if our maximum weight that the ski gondola is going to allow is 2,004 pounds. So 167 pounds is the maximum average we should have per person for this ride to be safe for 12 people to get up to go down the slopes. So here we want the probability that the sample mean, a sample of 12 men, is less than 167 pounds. We want each of those 12 men to be less than 167 pounds on average for this to be safe. So we're going to convert this into a z-score so that we can use our standard normal distribution table. So I'm going to do x bar minus mu over the standard deviation divided by the square root of the sample size. And this is negative 1.35. So the probability that z is less than negative 1.35 negative 1.35, 0.0885. Okay, so this is the probability that the ski gondola is under the max capacity. So there's only a 0.0885 chance, or a 9% chance, that the ski gondola is under the max capacity. That means there's like a 91% chance that the gondola is over max capacity. So this gondola is not safe. The probability that this gondola is safe is very, very low. This gondola is not safe at all. So if you wanted to see how this problem would need to change, or how this plaque should be rewritten to make this gondola safe for people to ride, you could go through the problem and try dividing by 11 people to find a new sample mean, and then recalculating it with 11 to see if that z-score has improved. Then try it with 10, and then see what that probability is. Try it with 9, try it with 8, and your goal is to get a probability that's as close to 1 as possible. You want it to be 100% safe, or 0.999. You want it to be really, really safe. So this right here, though, has a very low probability of being safe, and no one should be riding. Well, not no one, but definitely you should not have 12 people on that ski gondola at a time.